Oh, geez. Yeah, I love the excitement. All right, guys, let's do this. Yeah, so I think we're all familiar with the concept of arithmetization. You take some computation, you put this in the form of some kind of arithmetic circuit. This can be, in the form of addition and multiplication gates, like A, B. This goes down to, no, it's not a circle. It's not a gate. It's C with multiplied with D, and that might give you some output. Oh, or you might have, for instance, maybe an execution trace. So you have a table. It's not a table. This is a table. Where you have a series of steps, and then every step you might have a set of variables. I'll call these variables A, B, C, and you say A is like A's of I down to A's of J, B's of I down to B's of J, C's of I down to C's of J. And that's kind of like your steps, your computations, execution trace, and then you, at least in algebraic interpretation, you would then define a set of polynomial constraints that relate these to each other. And oftentimes we think, wait, am I saying this wrong? Or, okay, it's good. Please tell me I'm saying it wrong, because I'm also learning.
So this one is just the constraint.
Oh.
Each row is a constraint.
Yeah, but your intuition might be that these things are all the same, and that's what CCS kind of suggests to us, is that yes, these things are actually all the same, and we can define one single way to arithmetize different representations of the same sets of computation, and then we can define proof systems on top of this, which introduce no overhead relative to the original proving systems. And I'll kind of get into detail about what exactly that means, if I'm able to do so. Okay. Right. So yeah, let's start with kind of some of the claims being made in this paper. So the claim is you have
She told me not that one. Sorry.
Oh yeah. I'm not talking about ZooPass. Yeah. Yeah. Okay, so yeah, the claim you have, the claim is being made about 3 sets of representations. The claim is being R1CS. Claims being about Planck. Vanilla Planck. They don't get into to some of the other kinds of Plancks, and AIR. And they say, okay, for R1CS we have a Spartan and Marlin. For Planck we have, actually I think they do hyperplanck, so I guess they're doing it over the Boolean hypercube variable. And they also have vanilla Planck. And then for air, I think they also like to Spartan. Although I'm not too familiar with air, so I'm actually not sure if Spartan can prove air instances. But
I think A is for star.
air, yeah, but I think they mentioned in the paper, but weird.
Spartan is for R1CS.
Yeah, that's what I thought too, but because I skimmed this thing. So yeah. Okay, so let's assume this is not the case. But anyway, they basically like, okay, we have these proof systems, and now we're going to, they do 2 things. The first is they take these and they define new proof systems over CCS, super Spartan and super Marlin, and then hyperplanck and Planck. Actually, I think they just directly operate on these, but they instead of using the original implementation, they directly derive the polynomial coding from the CCS instance. And then for this, I don't know what they do, I guess, but I assume they did something. and then they also, at the very end of the paper, they define a new proof system called, oh, it's just called Super Marlin. Yeah, they're talking about Super Marlin out here. Okay, cool. Yeah. All right, so, and then we can get the hypernova with what she's talking about. Yeah.
So much high probability.
Yeah.
Build up for me, like whatever you can fail.
Yeah. Essentially, as I'll kind of show, air is especially good for uniform arithmetizations, and that kind of leads naturally into this discussion of folding. Yeah. So let me just erase all of that.
So you're trying to represent every one of that table, like what's the point of this thing about?
Oh, yeah. CCS is is a definition of an arithmetic scheme, and also the rest of the paper kind of goes into a derivation of how to map instances of every other arithmetic scheme onto this one, and also a proof that those mappings introduce no overhead in the pre-processing, no overhead in the actual mapping itself, and no overhead in the verification and the proving.
So the way to
Yeah.
map those stuff, like,
Yeah. Yeah. Okay, so what is CCS? I'll have to consult my notes for this. What? Yeah.
What is the full form of CCS?
I'm getting to it, okay? Just give me a second.
That's the standard.
Okay. Let's define a structure S.
You guys have those two.
Which is bounded by size bounds M and capital N, L, T, Q, D. L, T, Q, D, which are an element of the natural numbers, and also N is greater than L. And then we define features and matrices, which are defined over a field bounded by M and N. So you'd have matrices M0, M, T minus 1. Yeah, that's T right there. And they're all an element of the field F, which is bounded by M and N. And also, over the set of the whole matrices, you have most n non-zero elements, where n is equal to omega of the max of m and n. And just to remind you, omega is the multiplicity function. So essentially, if you take a number and you prime factorize it, like let's say you take 25 equals 5 squared, then omega is 2. And then 16 equals 2 squared, omega equals 4. Then you have some number like 3 squared times 2 squared. Then omega is also 4 because it's 3 times 2. So, yeah. So if you want to ask me why this is the case, I don't know.
What's going on here?
I'm just defining the constraints of CCS. Yeah.
Definition of CCS.
Yeah.
So there's no parameters.
Yeah.
First row is as constants.
Yeah.
Yeah.
They're all natural numbers. Yeah.
If this is what it is.
Oh, n is this. It's equal to the omega function of the max of m and n. Yeah.
Sorry, what's omega? I'm trying to understand omega, but I couldn't understand.
Oh yeah, omega is it's like the prime multiplicity thing. So you take any number and you prime factorize it, and then you sum the exponents over all the prime factors.
Okay.
Yeah.
Okay.
Yeah.
Why is big M?
What is what?
Why is big M?
I think it's coming to be M later.
Oh, m's are matrices.
Okay.
Yeah, each of dimension m times n. Yeah. Okay, yeah, and then Q is a sequence of and there's a sequence of Q multisets, where each element in the multiset is from the domain. Okay, yeah. So now we have Q multisets. S of 0, S of t minus 1. And as you know, a multiset is essentially I think of the set where each element can repeat. So if you have a normal set where it's like set element 1 and 2, it's fine. A multiset can be like, okay, that's not a bracket. That's also not a bracket. Jesus Christ. Okay. So let's say you have a single set. Generally speaking, the elements in the set cannot repeat. It's 1, 2, 5, whatever. A multi-set, the elements can repeat. So it can be 1, 1, 2, 4, 5. Yeah. So that's what a multi-set is. Yeah. So, and every element in each multiset is from the domain 0, t minus 1. So each s of 0 is a sequence of numbers like this from this domain 0, t minus 1, which you notice also the number of matrices you have. So these essentially act as, you might imagine, as ways to pick which matrices occur in which constraints in this very generic framework. Yeah, and finally you have a series of Q constants. Q. Okay, yeah, Q constants. We're almost done. Well, almost done with this definition, actually. But then you have to figure out the mappings. C0, C of Q minus 1. That's a bracket. That's the domain of each of these. Oh, sorry, those are the definitions of the constants. And each constant is in F. So I don't know why they don't define the dimension of F. I guess that's weird. Interesting. Yeah. Okay. Yeah. Oh, thank you. I'm just wondering why they don't define the dimension of F. No, I'm just trying to. I'm reading the next part so I can say it. Oh, it is. Oh, got it. So it can be infinite, or so the coefficient can be infinite, or
C0
yeah.
to C2 minus
Yeah.
1 is
F. All right, it's not dimensionality. Yeah. My bad. Yeah. That makes sense. Yeah. The order of F is not something which is defined here. Yeah. Okay. Cool. Yeah. So now we have our public inputs. We have X, which is an element of F. Okay. F of L. We have our witness vector W, which is an element of F of, yeah, exactly.
Oh, because RCS.
Yeah.
No,
Yeah.
It's only one thing. That's the only one thing I remember from the paper.
Yeah. And
RCS, right?
yeah, and then we define our full input vector as equal to, yeah, this is actually a set R1C. That's the same. It's the same input vector. Well, only this part. Yeah. W1 X. So basically your constraints are operating over a vector of size n, and the actual form of the constraint. So now we define Q constraints, which are defined by these Q multi-constants, and the actual form is, I'm going to draw the box first. And yeah. Nope, that's not a good sigma. No, sorry. Different variable. I equals 0. Then you have C of I. And this is a scalar multiplication times this, which denotes the Hadamard product of it's also Y? Yeah, it's also Y. Yeah, so you're defining it. And then, yeah, the matrix M of I times Z. And this equals 0. Yes, that's the CCS. So yeah, this is essentially a very generic form of describing an arithmetization scheme. As you can tell, it's like super general in the way it kind of sets things up. It's like, you could define any set of multisets, these matrices. Well, I guess these are all constrained to be m times n. And the rest of the paper kind of says, okay, now that we have this, let's derive a proofing system on top of this, and also let's show that the mappings are equivalent for ones. And I think I will just go through R1CS for the.
Can you go to air?
Wait, Hypernova goes on air? Is it?
You can convert air to CCS.
Oh no.
But I don't understand the math, so
No.
No,
Okay, I can't do that.
I respect it.
Yeah. I don't even understand how it's just like a set of polynomials. Yeah. It's not like an representation. It's more algebraic. Yeah.
What's that circle mean?
That's Hadamard product. So it's like see each of these matrices. So basically, if you multiply a matrix of size m times n times a vector of size n, you get a vector of size m, and then you're multiplying element-wise.
Oh, I
So
mean that big circle.
that means Hadamard product.
Oh,
That's what I'm saying.
okay.
Yeah. Yeah.
Okay. I see.
Yeah. So essentially, each one of these, you've got for every element in S of I, you are picking one of the M of I matrices. You're multiplying that by the input vector S, and then you're taking that entire set, and then you're pairwise multiplying together, and then you get a vector of size M instead of N, and then you multiply it by a constant, and then you add it all together, and that should all equal 0. Yeah. Yeah, it's super easy. Yeah.
And you flame the crowd at the end.
Yeah. Okay, yeah, so let's go through the R1CS bijection. Said that very competently. Okay, cool. So what's R1CS? As many people know, you have matrices A, B, and C, and input vector, the same notation, Z. That's not C. Then R1CS simply says A times Z. I guess use the same Hadamard product notation. I guess technically it would be. No, I'm not going to do that. Okay, I'm not going to use this. Okay. So yeah, so how is this equivalent to this? Just going to read for a second. So yeah, let's define m0 equal to A, m1 equal to B. Actually, it's pretty simple. Never mind. M2 is equal to C. And then you define your two multisets, S of 0 equals 0, 1, and S of 1 equal to 2. Yes, thank you. And then you define your constants, C0 equals 1, C1 equals -1, and it just kind of follows. Yeah. Mm-hmm. Yeah. That's the end of my talk. Yeah. All right, now take it away, Chi. Wait, sorry? Huh? What happened?
What is the big solve in the matrix?
Oh, that's Hadamard product again.
No, in the.
Oh, this is also Hadamard product. Yeah. Yeah. Okay, cool. So I hope you guys learned something.